Hello, everyone. We'll be starting in a few minutes. Give people a little bit more time to join. Hang on. We're not broadcasting yet. There we go. Hello, everyone. So we'll be starting in a few minutes' time. So I'll give people a few more minutes to join. But just to introduce myself while we wait. So my name is Robert. I've been product engineer at OxTS for about 2.5 years now. I'm joined on the call by Jamie, who's from our marketing department, so he'll help with the Q&A and also tell me if my mic stops working or any other technical issues. And so we'll be going through how to perform a lane departure warning or lane keep assist type test today. There'll be about 35 minutes of me talking and then about 10 minutes for Q&A at the end. So if you have any questions, please type them in the question box and we'll have time to go through those at the end. Hello, afternoon, everyone. Hope you're all keeping well. So to those who have just joined in the last few minutes, so my name is Robert Goff. I've been product engineer at OxTS for about 2.5 years now, and it's generally my role to basically keep up to date with all the changing Euro NCAP and other NCAP test protocols, making sure that with the roadmap and any changes ahead, that our products can still be good enough to give you the data that you need going forward. So today I'll be focusing on lane departure warning and lane keep assist type tests. There we go. So yeah, we are recording this, just so everyone's aware. So everyone who's on this call should have a download link to this shortly afterwards. It depends on how long it takes to physically upload the file to the site, but shortly afterwards you should have a download link to this, and there should be a copy of this on our website a little bit afterwards as well, which just needs trimming down me talking at the start. If you keep your microphone on mute throughout, if you have any questions, please type them in the question box. There'll be time for those at the end. Otherwise, I'll be talking for about 35 minutes and we should be done by about 4 o'clock UK time. So in terms of what I'll be talking about today, I'll start with just a brief overview of lane support systems in general, how they work, what the different technologies that make them up are, then how they're assessed, different test protocols around the world, major and smaller differences between each of the NCAPs, what that means for what equipment you need. So, for example, what the accuracies required are and how that dictates what we would suggest that you use. And then the bulk of the webinar will be how to physically perform these tests, either with our equipment or just in general with vehicle setup, etc. So just a brief overview of lane support systems in general. So both AEB and lane support systems both emerged around a similar sort of time in the early 2000s. In principle, they're not exactly related. So AEB generally have radar, LiDAR, more kind of measurement type devices to detect a physical object there, whereas lane support generally requires just a camera and sort of image processing and interpretation for what part of the image is a lane marking and so on. But broadly speaking, the sensors, the computing power to be able to do that in real time, coupled with things like drive-by-wire that enabled brake-by-wire and steering-by-wire, those all happen to come along at the same kind of time. So just as we saw AEB start to come around in the early 2000s, lane support and blind spot were around similar sort of time. So the first lane departure warning system itself was around in 2000. It was developed by a third-party company called Icarus for Mercedes trucks. And the first vehicle that I could find, as in passenger vehicle, was the Nissan Sima, which was around in 2001. I think it was just a JDM vehicle. But then they started to become slightly more common in Europe and throughout, generally more in high-end luxury cars such as the Volvo S80 in 2007. And then as technology moved on a little bit more and lane departure warning started to be linked with drive-by-wire technology and steering-by-wire, various different vehicles started to introduce it by about 2012, 2013. It's hard to say exactly which one was the first, but they all kind of came in a big lump in 2013. So in terms of how lane departure warning physically works, so as I mentioned earlier, this is purely a vision-based system. So it's not measuring anything because there's the painted road marks kind of don't reflect signals necessarily any differently to black asphalts, though arguably a little bit with LiDAR, but generally it's that these are camera-based systems where you have a camera mounted fairly high up, usually in front of the interior mirror, looking forward, projecting forward, and that camera input is then based on an internal calibration that will have been done at the factory, kind of transformed into kind of more of a top-down perspective. The bits that aren't relevant are discarded. So if the vehicle already knows what sort of angle the lane lines are in, it can discard anything above that or to the sides. Then conversion to grayscale, sexing candy edge and rough image transformations, then that basically helps determine where the lane lines are. So the key thing with all of this is that, as I mentioned earlier, because these aren't measurements, lane lines are something that you can see, but they don't physically exist in the same way that a vehicle or a lorry or something that a signal can bounce off does. So how accurate the systems are is basically down to how well this image processing works rather than specifically the sensor itself. The sensor itself is basically just a camera. And as such, depending on quite how well these algorithms are done, things like cracks in the road surface or merging lane markings, or when lane markings themselves get a little bit muddy or faded over time, they can be more easily confused than say AEB systems or cruise control, that kind of thing. And in addition, when they're detecting not just lane markings, but say the road edge, then there are lots of different types of road edge. Sometimes it's literally just the asphalt meets grass. It could be gravel. It could be different types of lane markings. It could be a pavement with a curb. So different types of lane marking and road edge needs to be detected, which all need to be kind of programmed into these algorithms. And when this works with steering by wire to steer the vehicle back into the lane, we call that lane keep assist rather than just a lane departure warning. Now, a related technology is blind spot monitoring. So we kind of put this into the same category as lane departure because generally these are technologies that are used when a driver is about to change lane. If a vehicle's in your blind spot, but you have no intention to change into their path, that's not necessarily a hazard. It's only when you don't see them and you might turn into their path. So when you might be changing lanes into them. So that's why you would generally have camera, radar, lidar, different sensor, different systems use different sensors, but some sensor that can detect an object is there, and then give the driver a warning, which is usually just displayed in the wing mirror, and they can see that, realize that there's a vehicle there, a hazard, and not steer into their path. Blind spot monitoring itself isn't actually that commonly tested as a standalone protocol. Korea NCAP have a specific protocol for testing blind spots, but they're about the only NCAP that do. What generally happens is that it's a technology that's incorporated into more scenario-based things. So, for example, Euro NCAP have what they call emergency lane keeping. So they have a few different scenarios that I'll come to, but one of which has an overtaking vehicle from behind. And in that scenario, the driver of the vehicle under test should attempt to turn into their path with the vehicle in that blind spot, and the vehicle under test should steer the vehicle back into the lane or warn the driver that something is there, which obviously incorporates blind spot monitoring, but isn't specifically referred to as a blind spot monitoring test. But the technology is still required to do that. So I mentioned earlier emergency lane keeping. This is basically down to something that Euro NCAP basically identified a need to kind of separate crossing a lane line, say on a highway, if there's no other vehicles around, 2 or 3 lanes, drifting briefly over the white line is still dangerous. It's not a good thing to do, but there's no threat necessarily there. There's no danger to life if there aren't any other vehicles present. So whilst it's useful to have a system that can warn the driver if they do that, such a system should be able to be turned off. But separately, if you were about to either leave the carriageway altogether or head over into the opposite carriageway with an oncoming vehicle, or if as a result of leaving the lane there was a concrete threat to life, either with an oncoming vehicle or leaving the road altogether, that was then classed as an emergency. And so Euro NCAP wanted to test emergency systems that would be always on, so you could turn off your lane departure warning but still have a system that will keep the driver safe in the case of emergency. And it was in this scenario that the blind spot system is tested. So in terms of how the systems in general are tested, I already touched on how Euro NCAP do this. So basic lane departure warning testing is done pretty much around the world. So the likes of Korea NCAP, Japan, NHTSA, Euro NCAP all have different protocols. Some are relatively straightforward. It basically is just drive the vehicle along the lane at a particular testing speed, and it just says steer left or right across the lane markings. Japan and Korea only test with a dashed white lane marking. NHTSA tests with a variety of different lane lines, such as a solid white line, a dashed yellow line, and also raised pavement markers, so cat's eyes as well. Whereas Euro NCAP only tests their lane departure warning with a dashed white line, but other lines are included in the emergency lane keeping protocol. Because generally in the UK and in Europe, a dashed white line is one that in principle is safe to cross as long as you carry out appropriate checks, but a solid white line is one that the driver should never cross because it's unsafe to do so. So I've mentioned emergency lane keeping a few times. So these are the 4 scenarios that Euro NCAP have identified. So they are basically leaving the road edge entirely, and there are 4 different specific tests for this. One basically with no markings at all, just where asphalt meets grass or gravel or something that clearly isn't asphalt. The same but with a painted center line, a dashed center line. Then the same again with a dashed center line and also a dashed road edge. And finally with a solid road edge. So in all scenarios, the vehicle should obviously detect that the road edge is there, and if the vehicle starts to veer in that direction, a correcting steering torque should be applied to steer the vehicle back onto the lane. The crossing a solid white line, this as I mentioned earlier, because a solid white line is generally only put in place where for example, if there's a blind corner or where it is unsafe to cross that line because of oncoming vehicles that potentially could not be seen. So in much the same way as the lane departure warning system would warn the driver it's about to cross a dashed line. If it's a solid white line, it should warn the driver and ideally steer the vehicle away to prevent it from crossing that white line. And finally, the last two scenarios, this is where the blind spot comes in. So essentially you have your vehicle under test, and with an oncoming vehicle scenario, you would have a vehicle coming in this direction as an oncoming vehicle. The vehicle under test would approach and start to cross the center line between the two, and then obviously the vehicle under test should then ideally steer itself back or warn the driver of the oncoming collision. And finally, with the overtaking vehicle, this is your classic blind spot scenario where you have a vehicle in the driver's blind spot but overtaking, so traveling faster than the vehicle under test. And if the vehicle under test travels into the next lane, then there would be a potential collision. So in both of these scenarios, because the impact point is with the front of the vehicle, obviously a towed soft target wouldn't be sufficient in this case, so you would need to use a robot platform with the standard, the GVT, the global vehicle target that Euro NCAP have identified, which looks a bit like this. This is the a 4A provide modeled on a Ford Fiesta, just a collapsible soft foam target that runs on a robot platform. So in terms of what equipment you actually need to perform these tests and what the accuracies are, in the top right, we've got, that's just a screen grab from the Euro NCAP protocol, which is pretty much identical to the requirements for AEB tests and other NCAPs as well, the likes of Australia, New Zealand NCAP, China NCAP, and so on, all basically specify the same sort of accuracies for more or less all of the ADAS tests. They basically relate to just to speed, position, heading, and rate of change of heading and rate of change of speed, also known as acceleration. So other measurements are less critical, but all of the measurement accuracies are basically kind of within these kind of limits. NHTSA and Japan NCAP use a slightly different system where they refer to the percentage of the full scale of the sensor, with obviously the absolute accuracy depending on what that full scale is. But for an RT and for most sort of commercial systems that would be used in this kind of setting, you would generally be looking at accuracies of this sort of order, because that's sort of what the sensors are generally configured for. So in terms of what we would recommend from our point of view, what would we suggest? The requirement of a 3 centimeter horizontal positional accuracy essentially necessitates an RTK receiver and a base station, because there is no way of getting centimeter level accuracy without those two things. The requirements to have high grade acceleration and yaw rate accuracies of 0.1 degree per second and 0.1 meter per second squared. Again, that requires a high grade IMU. You won't be able to get those from an IMU, sorry, a GNSS only solution, because whilst they can tell you where you are and they can average out position, they can't tell you instantaneous accelerations and angular rates in the way that an IMU can. The system itself needs to be mounted rigidly within the vehicle. What you don't want is for it to be recording motion that isn't associated with the vehicle itself. So for example, if it's rocking back and forth, then that data will suggest that the vehicle is rocking back and forth, which may potentially fail a test. So you obviously need it mounted rigidly, so any motion that the vehicle experiences is experienced by the IMU itself, but not the other way around. And the way that we suggest is we have the RT strut. There are other ways of mounting an RT within a vehicle, but the RT strut gives a nice way to be able to kind of swap the units in and out of vehicles. If you're testing multiple vehicles in a given day, you can quite easily take the equipment in and out, whereas more permanent installations are great for developing one particular system, if that's what you're doing. But if you're testing multiple systems, it can, the easiest way to swap units in and out is with the strut. That's the two things you need. well, one thing you will need in all circumstances is the survey trolley, because whilst the vision-based system in the vehicle will use something like a camera to detect where the lane markings are, because, as I said earlier, that is potentially prone to detecting cracks and bad markings and so on. So you need a separate system to verify where the lane markings are, and the only way to do that precisely is to physically survey the latitude and longitude of the lane line as you go along, which requires a survey trolley, and that way you have a map of the physical location of the lane lines, and you can compare that with the vision-based system from the vehicle. The only other thing that you may need on a hardware-wise, if you're doing the emergency lane keeping with the ToadSoft target, sorry, not ToadSoft target, the robot platform target, the GVT, so in order to work out the range to this target, you'll need a long-range Wi-Fi system we call the XLAN. So for those particular two scenarios for emergency lane keeping, you would need the Wi-Fi and also the vehicle-to-vehicle feature. Otherwise, all that you would need is the vehicle-to-lane RT Range Hunter option, which is a software feature that will enable you to calculate all of the vehicle-to-lane measurements that you need to perform this test. So in terms of physically performing the test, the process that you need to go through, the first thing you'll need to do is physically survey the lane itself. And the first step there will be to set up the base station, because to survey the lane, you need that to be done centimeter level accurate, which means that the lane survey itself has to be in RTK. So because the base station takes a few minutes just to average its position, the easiest thing to do is to set that up and then configure the RT while it's averaging. If you then put the RT onto the survey trolley, plug in the user cable, take the radio modem from the base station and attach the antenna to the trolley and plug the modem into the user cable. And then what you'll want to do is power it on. So the survey trolley comes with a battery to power the RT. So that should enable you to power the RT, and you can use a laptop to connect over Ethernet to nav config. And you'll just want to load, there's a standard configuration, because the mounting of the RT on the survey trolley is the exact same point. So there's a defined configuration that you can load. There should be no need to measure anything. You can just load the survey trolley configuration to the unit and it will be fully set up. Then you'll want to initialize the system, which just requires moving it to, say, 1 meter per second or greater, and just to give it a forward velocity, and it will start outputting data. Then you'll want to position the survey trolley at the start of the lane line, and then you'll just push the trolley along the lane. Then you've got a couple of options for mapping the points. The first thing to do, or what you can do, notice there's a red button by the handle on the survey trolley itself. Each time you press that, it will add a point, and the line is just defined based on a series of points, and it will just draw a line connecting those points. Alternatively, what you can do is you can, in the software, manually select add point here, or you can just tell it to add points every, say, 1 or 2 meters or every second. Those values can be fully configured in the software. We'll generally say for a nice straight line, unless the line itself, say it's been badly painted and it's kind of quite wiggly, but assuming that it's a well-painted straight line, you probably only need points sort of a handful of meters apart. That will give you kind of a nice, smooth, solid line that will give you data that isn't too noisy. Otherwise, what you need to do is obviously detect the true path of the line. So if you do have a slightly strangely painted line, that's what the vehicle will pick up. So you do still need to survey that in and perhaps use more points to define that. And for a curve, you'll want slightly more points as well to get a nice smooth curve. Then when you've added all those points, you can save those points to a line file. Then if you open the map creation tool, you can save all of the line files that you've created, up to 8 of them, into a map file, and then you can have a map of up to 8 of those lines. So that can be useful if you're modeling like a highway scenario with multiple lines in the same map. Then with the lines mapped, you need to set up the RT. So you'll want to take the RT out of the survey trolley, put the strut into the vehicle under test, and put the RT onto the strut, moving the radio modem and antenna as well. And then in the same way, you'll want to power the RT, open navconfig again, and make sure you change the configuration, because it will probably be oriented in a different way to how it was on the survey trolley, and certainly the antenna lever arms will be different. So you'll want to measure the distance from the RT to the antennas and make a note of the orientation of the RT on the struts as well. The differential corrections should be left the same if it was working on the survey trolley. It should keep working in the car. And whilst you're measuring, now is a good time to also measure the distance from the RT to the outside edges of the front tires. This is because generally when a vehicle crosses a lane line, it's defined as the precise moment of crossing the lane line is defined as when the outside edge of the tire crosses the outside edge of the line, the lane line. So to be able to work out what that point is, you need to calculate 3 points: the outside edges of the left and right tires, the front tires, and so those are points A and C. We refer to them as, and point B is some point along the center line of the vehicle, which is useful to help if you have, for example, a lane centering system and you want to check that the distance from the center of the vehicle to the lines left and right of it is roughly the same. That's where it's useful to have that middle point. If you're performing an emergency lane keeping test, you'll also want to measure the vehicle polygon at this point, which I won't go into too much detail because there's probably a whole webinar in that in itself. If you're doing anything with robot platforms or vehicle targets in this kind of setting, either send me a message if you want more information, or we'll be doing some webinars on that kind of topic next month, so please come along to those. Then to set up the RT range itself, for a basic lane departure warning test, there's not too much else you need to do. If you just open the RT range software, there are no targets because it's just one vehicle and some lanes. Enter the measurements that you just measured for points A, B, and C in the lane measurements tab, and then load the configuration to the unit. That's essentially all that you need to do. For emergency lane keeping, it's slightly more complex. This is because for the final two scenarios where you're using a robot platform, you'll need to configure the system with one target for the robot platform, and then you'll want to set the target as a moving target looking at the IP of the robot platform itself. Then you'll need to configure both the vehicle under test and the target with full polygons, perform the same steps as you did before for the lane measurements tab. And lastly, after you've done the warm-up, you'll need to configure local coordinates as well for the polygons to work correctly. Local coordinates are something that you may or may not need. If you have if there's a requirement to have, say, a lateral path measurement, if there's a defined test path, then you will need to set local coordinates, which is essentially a local coordinate frame. So rather than north and east, you define an origin point, you define an axis, and you can then have forward and lateral of that that origin in that particular axis. It's more useful generally for AEB systems or AEB tests, which always require this. Generally for lane departure warning, it's simply the distance to the lane line that matters, so you don't often need to do this, but for emergency lane keeping, it will be a requirement. And also for emergency lane keeping, once you've configured everything else, you'll want to apply longitudinal lateral offsets to the robot platform, the target, to make sure that you're centimeter accurate for that. Again, I can elaborate on that a little bit more if you like, but it's probably another topic in itself. Then the warm-up, which I mentioned earlier. So with the system configured, to get the system up and running and into configuration, there's a couple of steps you need to do. The first is basically to give it a defined forward direction. When you first power on the RT, it records gravity downwards from the accelerometers, so it knows which direction is down, but it doesn't know which direction is forward. It could be pointing in any direction. So it works this out basically by you driving forwards, and as you cross a certain speed threshold that's defined in the configuration, usually say 2, 5, 10, something like that meters per second, the direction you're heading as you cross that speed is then defined as the forward direction. That can be improved slightly as the warm-up goes on, but it's kind of the initial configuration that the system needs. Then what it needs to do is correct for any errors in the configuration itself. So because the system is accurate to 0.1 degrees for heading and 0.03 degrees pitch and roll, the chances are you might have configured it roughly orthogonally within the vehicle, but there might be kind of, say, a degree out in yaw and maybe half a degree in pitch or roll or something like that. To be able to give you your full 0.1 degree accuracy in the vehicle frame, the system needs to correct for any errors there. And the way it does that is by you driving around, giving it a series of dynamic motions that will make the vehicle pitch and roll and accelerate and decelerate, so accelerate in different directions. And all of these things will help the system to refine much more precisely the configuration. So it'll be able to calculate the lever arms, which is the distance to the antennas, to within a few centimeters, the slip and pitch offsets, which will determine its orientation within the vehicle. Those will get down to fractions of a degree, and that will then get you the system in specification. Once you've done that, you'll want to make sure that you save that improved configuration to the device. This is because otherwise you might have, once you've done this, it will then mean that any further times you do any testing, it will be a slightly quicker warm-up because it will already have a smaller search space for its orientation and configuration within the unit, within the vehicle. As for setting up the vehicle itself, Euro NCAP specify that if there are any configurations for how early the lane departure warning system should intervene, it should always be set on the middle setting or the one after that if there's an even number. And also the test should always be conducted with a vehicle approximately fully loaded, so not overloaded, but say it's kind of, if you imagine the vehicle with a full tank of fuel and a spare wheel and 4 passengers, that would generally equate to about 200 kilograms of extra load. So that's what's used for the test. So generally the best way to do this is to rim the tank, make sure the spare wheel, if it comes with one, obviously not many cars come with spare wheels these days, but the tyre filler kit, toolkit, whatever standard kit comes with the car should be fitted. Then it should be weighed, and that will determine the curb weight. And let's say that's 1.8 kilograms, no, 1.8 tons even. Then you should get the test driver and all the test equipment installed in the vehicle. And if that comes to say 1.9 tons, you then have 100 kilograms of ballast to make up that extra 200 kilograms. So that way it'll correct for using heavier equipment or a heavier test driver or whatever. And lastly, the Euro NCAP specify that a series of braking and acceleration maneuvers, so circular driving and figure of eights and that sort of thing, should be used to condition the tires and the brakes. This is because most of the time these tests will be conducted with new tires, new brakes, and that shouldn't bias the results. But whilst the warm-up of the RT is obviously an important step that takes a little bit of time, because it's a requirement that the brakes and tires also be conditioned by Euro NCAP, this maneuver itself can actually function very well as a warm-up. So it's probably simplest to install the RT and configure it, install ensure that the vehicle is at weight and configured in terms of the settings, and then the brake and tyre conditioning can be done as part of the warm-up, and both will be done together at the same time. So the RT warm-up doesn't have to be an extra step that takes longer, because you would have to do these maneuvers anyway to adhere to the protocol. Then to perform the test itself, fairly straightforward. You'll basically just go to the start line, accelerate smoothly up to the testing speed, which depending on protocol will be some tests at 60 kilometers an hour, some 72, some 70, but all in that sort of range. And then drive the vehicle in a straight line parallel to the lane markings, and at the particular testing point, apply a certain defined steering torque or lateral velocity, which will generally be done with the steering robot. Quite often, certainly the Euro NCAP ones are quite precisely prescribed, so you can either have sort of markings on the steering wheel and sort of a precise amount of time to get to that point, but whilst it's possible for some of these to be done with a human driver, more commonly you'll certainly find the Euro NCAP ones will be done with a steering robot. But whichever is done, obviously the RT works with both human drivers and with robots as well. Then with the vehicle leaving the standard parallel path, whatever lateral velocity is required, the RT range will then give you all the data for longitudinal lateral velocities, heading, change of heading, distance to the lane, and all of these measurements, and obviously the precise point at which the vehicle crosses the lane markings, if it does. So to give you all of that data, the RT range suite itself, the RT range software has a real-time data display. So if you hit open display page, there's a pre-made, pre-configured display window with all the measurements that you need for this kind of test. You can configure that if you like by hitting configure display, and you can delete measurements, add new ones in. These measurements can also include, say, measurement accuracies. So if you want to make sure that as you do a test, any particular measurement that you're given is of the required accuracy, that all the tests you're doing has valid data, you can also add that in. So things like position accuracy or velocity accuracy or whatever it may be, you can have those accuracies stated alongside all the other measurements in real time. Then in terms of actually logging the data, if you do nothing, the data will still be there, nothing will be lost. We're quite paranoid about making sure that whenever you do any testing, regardless of whether it's ADAS or otherwise with our equipment, what you don't end up with is a wasted day with no data. All the data will always be logged, both to the RT itself, and also the range data will be logged to itself as well. But what you'll find if you don't specify anything else is that your whole day's testing will result in one long RCOM is the file format, but one long file containing every test that you've done that day. If you want to have specific files for a specific test, you'll want to hit start logging and stop logging at the end of each test. Or what you can also do is automate this process a little bit by using nav display rather than RT range, which has a function called test and save. It's in the utilities menu, opens up a window like this. You choose where to save the file, and in the start and stop tabs, you can basically configure certain parameters that will start and stop the logging of the data. So for example, if you're testing at 60 kilometers an hour, you can say start logging as at when the vehicle speed exceeds 55 kilometers an hour as a rising edge, and stop logging when the vehicle speed hits, say, 10 kilometers an hour on a falling edge. So whatever parameters you choose are entirely up to you. You need to be a little bit careful to make sure that you choose parameters that will always be hit. So don't say vehicle speed must be above 61 if you testing exactly at 60, otherwise it won't start logging until the vehicle actually crosses 61. But if you're careful with those parameters, you can basically fully automate that process, which is a little bit easier than having the engineer having to manually keep the software open and hit start and stop logging each time. But essentially that should give you all the data that you need. Anything I can help with? Any further information, details, anything I can clarify?
So thank you, Robert. Very good presentation. Thank you everyone for joining. We haven't had any questions just now, but if you do have any, use the chat box on the right of your screen. Just put those in. I guess while we wait to see if there are any, just to point out really that there are some other webinars coming up that are similar to this. So Robert, you'll be doing a webinar on AEB with braking and moving targets, and also some park assist testing as well in the next few weeks. So if you're interested in that, it's www.oxts.com, and you can see all of the webinars that are available there. So we haven't had any questions just yet, but so the recording will go out within 24 hours. You'll receive that via email. If you watch the session again, you have any further questions, then please info at OxTS, it says on the screen there, is that, and Robert will be happy to follow up. So it looks like we have had a question. If we have a full set of OxTS for an AEB car-to-car test, can they do the lane keep test? The LKP test, yeah. Sorry.
So the only things that you may potentially need are the survey trolley to survey the lane markings accurately. It is possible to survey lanes without the survey trolley itself. The way to do this is basically what you need to do is in nav config, in the advanced options, there's a way to displace the output of the RT to some other point, and you can do, for example, the outside edge of one of the tires, and then if you drive the vehicle along with that outside edge on the lane marking, that will basically record the path that particularly outside edge of that tire takes will be recorded as the lane. Obviously, the downside of that is that it's a lot less accurate to drive a vehicle centimetre accurate on a lane marking than it is to manually put a survey trolley. So for Euro NCAP standard testing, it probably wouldn't be good enough. For a sort of fairly quick and dirty sort of, you just want to check something sort of test, it can be good enough, but you'll probably want to have the survey trolley to do it properly. Otherwise, equipment-wise, if you've got enough to do a car-to-car rear stationary or even moving test, that's pretty much all that you require. Only other thing is if you have the new RTs, the RT3000 V3s with RT range on board, if you have that configured for an AEB test, that you may only have the vehicle-to-vehicle feature code. To do a lane keep assist test, you'll need the vehicle to lane feature code as well, but that can be added, it's just software. But otherwise, one RT can be used for either test. You don't need an extra whole load of equipment, basically just an extra feature code and an accessory in the form of the survey trolley will be all that you'd need.
Great, thank you, Robert. And I guess if you have any further information, or want any further information on the survey trolley, I think we're happy to follow up with you afterwards on that one. So if there's any other questions we've got a few minutes left. I think we're happy to stay here, so we'll be on the line until the time's up. So if you do have any other questions, please put them in the comments box and we'll answer them.
And just while I wait for any more questions, just one thing I'd just add is that with the other webinars that we'll be doing next month for Park Assist and for AEB, car-to-car, rear moving and braking, because both of those tests require target vehicles rather than just lane markings, we'll be going through some concepts such as vehicle polygons and that kind of thing. So if you were doing any emergency lane keeping tests with the robot platforms and you want to know how to set up a range system with target vehicles as well as just lane markings. A lot of the concepts I'll be going through next month will be transferable, so that some of those might be useful.
Okay, Robert, we've had another question, which is it possible to do the LSS tests with oncoming vehicles using the steering robot?
Yeah. So essentially, I mean, as I say, for a lot of these lane support tests, you probably will have the steering robot anyway to be able to do the steering either out of the lane. In terms of with an oncoming vehicle, it doesn't necessarily have to be a platform robot. Obviously, the danger of doing it with a real vehicle is if there was a collision. Obviously, a soft target on a robot platform is safe to collide with if it's a real vehicle. If the steering robot has an ability to steer the target out of the way at the last moment, that could possibly be work. But so in principle, yes, you absolutely could. But from a safety point of view, it's generally better to do the emergency lane keeping ones with the soft platform, just in case anything goes wrong with the test itself. We had another question. Is there a tool software for the automatic evaluation of lane keeping systems? So what we can offer basically is obviously all the data for the test itself will be logged by the system and will be displayed in real time. It's the protocols themselves that will define what a pass fail or what the kind of how many marks a given test is. So you can kind of configure the software to define what am I saying? Say if a pass is required to keep the vehicle within, say, more than 10 centimeters from the lane. If it goes beyond 10 centimeters, you can kind of mark a line on the software, and if it dips below that, you can see it's an instant fail. So it's not so much a specific tool. You can see it quite easily in the software because of things we've done, but we are also developing what we there's actually a software project currently called the ADS test utility that will have more of that automated pass fail sort of thing on there. So that's something that will be coming, but you can sort of do it by the way the data is displayed in real time in any case.
Yeah, it will just automate that, give more kind of at a glance for those kind of set protocols, isn't it? And one other question there is the position accuracy, etc., logged, or is it only displayed in real time?
Yep. So all of the measurements that you can see in real time are also logged to the unit as well. So which includes measurements such as positional accuracy as well as just position. So you don't just have to look at the data in real time to check that it's good enough. You can also load it in our graphing software, NavGraph. You can play the file back. You can monitor those measurements and just verify that at every point the measurement or the position accuracy, whatever accuracy it was that you care about, you can verify because it's all logged.
Excellent, thank you. And so that's sort of just taken us past the hour mark. And there's not any questions at the moment I can see. So I guess if we leave it there, and if there are any other questions, either because you watch the recording back or you just think of one, info@oxts.com will reach us. We'll be able to answer any questions offline for you. But other than that, I think all that remains to be said is thank you, Rob, for a great presentation. Thank you, everybody, for joining. And we hope to see you on another one soon.
Okay, yep. So thanks, Jamie. Thanks, everyone, for coming, and thanks for the questions. So great to talk to you again. Hopefully we'll see you on some of the ones we'll be doing next month. And so thanks again, and goodbye.